Hello everybody and welcome to episode 18 of our video series in which we program an entire video game from scratch, from beginning to end, with no engines and practically no libraries, just our own brains and the C programming language. Let's see, where were we last time? We were at a really good stopping point last time where we basically drew the beginnings of our animation, and we were walking around, and in every direction it looks pretty good except for when we go to the right. It's messed up. Our animation looks kind of funny whenever it's moving to the right, and our dude also ends up on the wrong, like he's not in a neutral position right now when we're just standing there. So that's obviously messed up. And that brings me to, as usual, before we get started and before we fix this, I want to get into the viewer comments that I received since last time. Let's see, where am I? Let me pull them up real quick. Okay, received a few. The first one is, this viewer says, awesome work. Thanks. Keep up the good work. Thanks for the ASCII Flow website, by the way. It's a really handy tool. Yes, it is. One of my coworkers showed it to me at work the other day, and I really like it. So I think the next step would be, like, I've considered getting one of those tablets that I can draw on with a pencil that would be on screen, so you could, when I'm trying to explain things, I could just draw on it the way that you would draw someone would draw on a whiteboard. Maybe I will. I'm not sure I'm ready to go that far yet, though. So for now, that's what I'm using the ASCII Flow website for, is just to explain things. All right, next viewer says, pound define direction right 6 should fix your right-facing animation, since 6 is the index of your right-faced standing still bitmap. So let's go see what he's talking about. Yeah, so if you recall last time when I was originally writing this, and I was like, this doesn't feel right. And I think this is exactly what I thought didn't feel right. And now it feels much better. 0369. That seems much more sensible since it goes up by 3 each time. Sounds like exactly like where it should be. So let's run it and see what happens. Yeah, that's exactly right. So now our walking to the right animation is correct. Our walking to the left animation is correct. Our walking up and walking down, everything is correct now. So first of all, thank you for that. And this is working out really well. This is exactly what I wanted, was for you guys to come and help me find my bugs. That's perfect. So thanks again. Next viewer says, shouldn't we already start structurizing the code? And what I mean is to make new files and folders. For example, putting the window function and related into a separate file, because later on it may be quite time consuming to organize it. Yeah, so he's talking about making, like, if we made another C file in here and called it something else. Basically, as your project gets larger, it starts getting more and more cluttered. I mean, this C file that we have right here is only 187 lines right now, and of that, there's probably half of it is actual code. So, there's probably something like 100 actual lines of code in this file, because most of them is, because I do the double spacing thing. So. Oh wait, sorry, that's my H file. In my C file we have 927. So probably, oh, you know what it'll tell me? GitHub will tell me how many actual lines of code, not counting the empty lines I have. So if I go to GitHub right here and look at our repository and click on main.c, it will tell me I have 628 lines of code according to GitHub. And I don't know all of the algorithm that GitHub uses to calculate that, like if it's calculating, like this, for example, could be one line because it's, you know, simply it's one single function call. I just chose to put it on basically 5 different lines because it would be messy. It felt kind of messy to string it out all the way across the screen. So I don't know if GitHub counts this as 1 line or 5 lines. Also, I don't know if it's counting comments like that right there. I don't know if that counts. So forth and so on. But anyway, I digress. The point I'm trying to make is this is not very big yet. This project is not very big yet, and that's why I haven't bothered breaking this out into separate files. As the project evolves and gets bigger, typically what programmers do is they will start breaking their functions into separate C files and their definitions into separate H files, and they'll keep related things grouped together. But I haven't. I'll do that eventually. I'll definitely do that eventually, but I haven't thought about doing it yet. And I typically don't do it until I start feeling the cognitive load of not doing that. What I mean is, when I start feeling like, when this starts feeling cluttered to me, then I'll start thinking about breaking it up into multiple files. I feel like to do it now would be premature, and you know, there's already, we've not even written 1,000 lines of code yet. There are already many different things that we could do to optimize the code that we've already written, but I feel like that would be premature. And I'm sure that many of you have already heard the age-old adage that, you know, premature optimization is the root of all evil in programming. So that's kind of where I stand on that. Is that, yeah, of course I want to break the code apart into separate files at some point. I just haven't done it yet because it just feels too early. So I'll do it later. Okay, so next viewer says, "Hi, this is amazing. I was wondering if I could do this on a Mac." On a Mac. So technically, it's possible. Of course, most of what we are doing here is portable C code that will run anywhere on any machine. C, it's one of the beautiful things about it, you know, was invented in the 70s and now runs on almost every machine that has a microprocessor of any kind, anywhere in the world, from not only your Windows 10 gaming PC to your toaster oven to the microcontroller that sits behind the buttons in the elevator when you press the buttons. All these things run C. Everything runs C. But the things that won't work out of the box is like right here, for example, where I'm calling API functions. Here's another example where stretch di bits, and another example would be like in the load bitmap function where we call create file. Those are all examples of API calls where we interface with the operating system. Those would all have to be changed if you're going to port this to any other operating system, be it Mac OS or Linux or whatever. We're going to have to port anywhere where we interface with the operating system are the things that we're going to have to change. The rest of the stuff, however, for example, if I go to, Blit 32-bit bitmap to buffer, like this function right here, this function ought to be really, really, really portable, considering all we're doing is copying bits into memory. And that code should be practically portable universally anywhere. So, okay. Next question. Next viewer says, hey Ryan, I'm currently working on a side project in order to understand the Win32 API. I was wondering if you knew by any chance how I could enable support for C++11 compilation in Visual Studio, because I don't want to use C++14 or 17 yet. Thanks in advance. Okay. So obviously, if you've been watching this video series for any amount of time, you know that we're not using C++ at all. We're using just C. However, I think I can take a stab at this question anyway. The short answer is no. You can't do that. The long answer is now, like I said, we're not using C++, but just imagine for a second that we were. If I go to if I go to my project properties over here, and then I go to C++, and then go down to language, the language page, I have this little thing right here, this little option here that says C++ language standard, and right now it's on default, and I have options that say I can use the C++14 standard or the C++17 standard, or I can use C++ latest. So whatever preview features they're working on for right now. There is no option for C++11 standard though. So what he's asking basically is he wants to restrict himself to only the features that existed in C++ up to the 2011, the year 2011 standard, and nothing newer. So, which is a valid thing to want to do, because new features, be it C++ or C or any other language, just because they're standardized doesn't mean that they are bug free. It doesn't mean that those features were well thought out. It doesn't mean that those features are necessarily something that you want to use. So, I mean, I've heard some programmers say that some of the features in C99, which is the C 1999 standard, 21 years ago, I've heard programmers say that some of those features are quote unquote immature. So, take that how you will. Anyway, so this is the /std or /standard switch in the compiler. It's a compiler switch, and if you look this up, let's see, let me pull up MSVC std switch. It's documented, and basically, you can specify C++14, 17, or latest. There's no C++11. In fact, if you go to the Wikipedia page, the Wikipedia article for Visual Studio, you will see that in Visual Studio 2015 is when they introduced this /std switch, and even in Visual Studio 2015 they did not have a C++11 switch, a C++11 option for this STD or language standard switch. So I think in 2015 the status of how much or how compatible Visual Studio was with the C++11 standard, even then I doubt Visual Studio was 100%. I doubt that they had implemented 100% of the C++11 standard by that point. But that being said, so the long answer is, I think if you find an older compiler, Like if you went and found like an older version of Visual Studio, even older than 2015, you might be able to restrict yourself to only the C++11 standard. Or if you use some other compiler, you know, I don't know if like GCC has a switch that does it or something like this, but there are definitely other compilers out there that you're free to try. I don't know if they do a better job of this or not, but in Visual Studio, no, not really. There's not a way to artificially restrict yourself to C++11 specifically. Okay, so I think that's the end of the questions. Now, back to the code. So what do we want to do next is the question. We're walking around, animation's looking good. I think the next step is going to be text. And I'm pretty excited about that because once we've got text, then we can do all sorts of things, like we can replace all this debug stuff up here so that we don't have to make those calls to the Windows operating system to draw text for us anymore. We can also do things like draw our own menus and dialog boxes and all sorts of cool stuff. Cool stuff that we definitely 100% need in order to progress with this game. So yeah, onward with text. So what I think I'm going to do is make a new function. And I'm going to call it, it's going to be another blitting function because it's going to blit bits onto the screen effectively. And I'm going to call it string to buffer. And it's going to take another game bitmap. And what I like about that is that we're reusing the same data structures. We don't have to introduce any new concepts. We're just getting to do the exact same stuff that we were doing before with the game bitmaps that we're already familiar with. And it's going to look just like our blit 32 bits per pixel bitmap to buffer function, in that it's just going to take an x and a y coordinate, and we're just going to be able to blit a string there. Talking and typing at the same time, not my forte. Not my forte. Okay, x and y. Blit string to buffer. Takes in a game bitmap pointer, an x and a y. Okay, and we're going to go and we're going to make this function happen. Let's try to keep them in order though. I want it to, this goes right above the render frame graphics function. Okay. So before we proceed to do this, we need a game bitmap. We need to load a game bitmap, which we already know how to do, but this game bitmap needs to contain our font, our letters, our characters that we're going to use to draw text. So I got a little something over here. Let me find it. I think this is it right here. Let's see, copy. Our source repos, assets, paste. There we go. 6x7 font.bmpx. Recall that our BMPX file format is specifically a 32 bits per pixel bitmap, and as we talked about before, the 32 bits per pixel bitmap has the negative of taking up a lot of disk space, but it has the positive of having an extremely simple file format that is both easy to load from disk and it's easy to work with in our code. So that's why I use it. So let me open this up. So what we have here is a 32-bit bitmap that contains a font. And I drew this myself, and this is all the letters of the alphabet and some symbols, just how big is this? So there we go, bounding rectangle size 6 by 7. So each one of these characters is 6 pixels by 7 pixels. And I think, and I'm not, I don't quote me on this because I painstakingly drew this myself, and I think it's about the smallest legible font possible. If you think you can find a smaller font, let me know, because I probably would be interested in that. But this one is the smallest font that I could draw and still look okay. It's quite tiny. It's quite pixelated, which is perfect for our needs. It's exactly what we wanted, because we're drawing a very pixelated game. We want a purposely pixelated font. All right, so it's going to look just like that. If I go do a search on like NES Font Sheet. Font sheet is a really common term that you'll hear a lot of in the retro gaming sort of sphere, and there's 100,000 examples like this of different fonts that are laid out in such a way that you can load them into your game and process them. Now, the way I'm doing it here notice how all my letters are on a single line? I'm literally just like doing the whole thing on one line. I don't think anyone else does it like that. Most everyone else does it in a grid like this, where it's a certain number of characters across and then a certain number of characters high. It doesn't matter. You do it however you want to do it, in whatever configuration you want to do it. It's just like, I felt like there was nothing stopping me from just drawing all these characters on one line, so that's what I did. I think it's just, yeah, I mean, there's not really any reason. This one's kind of cool because this image is kind of cool because it shows examples from real life NES games. But yeah, that's just grab something here, something like this that makes sense to you. If you don't want to draw your own, you just need a font sheet. So this is my quote-unquote font sheet that I have come up with. It's 32 bits per pixel. It has a transparent background, and now it's black. It's actually black text. If I wanted to make the text white, then I'll have to enhance this function at some point to say like what color I want the text to be. But for right now, we'll start simple. So anyway, first thing we need to do is load that bitmap that I just showed you, 6x7 font.bmpx, and this is the code we need right here. However, I'm just going to copy this. I'm going to copy this, but it's not part of initialize hero, so let's just back up and put it somewhere like in WinMain. Let's make a global variable, a game bitmap, and call it G 6x7 font. I don't know how many fonts we're going to have in this game. This may be the only font that we have, but I don't know that for sure. We might have fonts that are bigger. We might have fonts that that have maybe some anti-aliasing to them. I don't know yet. But this is the most basic font that we're going to start with. So now we've created this global. We need to populate it with some actual bitmap. We need to load the bitmap into that global variable, which I suppose I can do somewhere here in WinMain. And six by 7 font.bmpx, and we are going to load that into G 6 by 7 font. Now, if this function does not equal error success, then we failed and we will exit the game. Okay, does it work? Yes, it works. Okay, now we have our font loaded. So let's go here. And what do we need to do? All right, so one other thing is how many characters are, if we go in back here and look at the number of characters, let's see, it's 588 pixels wide. So 588 divided by 6 is 98. So there's 98 characters on this thing, on this line, 98 characters. So let's go ahead and put that in a pound defined. We'll put it font sheet characters per row 98. And this might come in handy if we ever use other fonts. So we might switch to some other format. I don't know. But we're going to need that number to do our math. So let's see. First thing I'm going to do is, oh, wow, I totally forgot. We have this function called BlitStringToBuffer, but you know what we never actually supplied was the string that we want to actually draw onto the screen. How silly of us. Okay, so we're taking in a pointer to a string, pointer to an array of characters to draw onto the screen. Okay, so I will update that, and now we're good to go. So let's see, character width equals. So our font sheet width, which we know is 588 pixels, is game bitmap info BMI header dot BI width divided by font sheet characters per row. So this will be 500. This number will be 588 because that's the width of our bitmap. This number is 98. That's how many characters we have per row. We only have one row on this font sheet, and so the result is the width of 6, right? 588, yeah, divided by 6. So the result will be 6. That will be character width. Okay. Char height equals Okay, we need, well, it's just the, let's see, game bitmap info bmi header.bi height. In this instance, since we only have one row, the character is going to be the height of one row, which is the height of our entire thing, of our entire bitmap. Okay, so let's see, let's make another one called bytes per character equals char width times char height, and then times. So we could do this a couple ways. We know that this is a 32-bit per pixel bitmap. If we were wanting to be really thorough, let's just do game bitmap bit count, bi bit count divided by 8. Okay, so bytes per character is basically the character width times the character height times 4, which is 32 bits divided by 8, which is 4 bytes per pixel. Okay, and then of course string length is going to be strlen string. And then later on, we'll probably put some error checking in here that's like if, string length is less than 1 or string length is greater than 1024 or something like this. Then at that point, we'll probably just be like, we'll assert, basically crash the game or something. But for right now, I'm going to leave the error checking or input validation part out of it. We'll do that later. All right, so we need to create a game bitmap. We need to create a new game bitmap called something like string bitmap. So what we're going to do is we're going to create a new temporary game bitmap. We're going to take the string that the user wants to draw. We're going to draw that into the temporary string bitmap. We're going to literally string the characters together in the order that the user wants them to make a readable, to make text, to make strings. And then once we have that temporary string bitmap, we're going to then use the function that we've already written to blit that into the buffer using our blit bitmap into buffer function that we've already written. So shouldn't be too hard. We need to basically fill out our bitmap. Bitmap info bmi header bi bit count equals game bits per pixel, which is 32. Height bi height equals char height equals char height. String bitmap dot info. Okay, the width of this thing is going to be the width of the character times how many characters. So string length. That's how wide the thing is going to be. What else? String bitmap dot bitmap info dot bmi header dot bi planes equals 1. String bitmap dot bitmap bmi header dot, what have we not done yet? Bi compression equals bi RGB. Okay, and then finally, string bitmap.memory is going to be where this is where we're allocating memory for our temporary string bitmap. We're going to use heap alloc just as we have in the past, and the heap is get process heap, just our regular process heap. Flags, I guess, is like heap 0 memory, and then the how much memory do we want? We want bytes per character times the number of characters, right? So string length. Okay, and we will assume that that succeeded, that heap alloc. So one thing that I like to do is anytime that I write heap alloc, you instantly know that at some point you're going to need to free this memory, right? So heap free. Probably no flags, and then the memory that we're trying to free. I think that's right. All right, so, and this will be somewhere at the bottom of our function. But I didn't want to forget it, because when you're in the heat of the moment, you know, you might forget to free your memory, and before you know it, you've got like this huge memory leak that's difficult to debug. So okay, so now we need a for loop that basically iterates through each character that we're going to draw. So we're going to do, and I'm also going to something else I'm going to do is when I go back through this function and clean it up, I'm going to more appropriately size all these things, because I don't think they all need to be ints. They probably need to be like, you know, uint 16 or something like this. I don't think it really matters right now though. So let's just keep going. For character is less than string length. Why can't I draw? Okay. Now, just as we did when we were writing our Blit 32-bit bitmap, we need to calculate offsets where we start drawing. Specifically, we need to calculate, like, say for example, the user wanted to print the screen. Let's say for example we wanted to print the string game over, like you died, it's game over. The first letter in that is the letter G. So we go over here and we find capital letter G. We basically need to know how many bytes of memory into this bitmap do I need to go, or how many pixels into this bitmap do I need to go to find the letter G. That's all. So that's what we're going to do. Int starting font sheet byte. Font sheet offset. And then we're going to make a pixel. Font sheet pixel. Now what we need to do is I want to basically write a gigantic switch block. for every character. So every time we go through this loop, we need to determine what character actually are we trying to print to the screen. So I'm going to literally just start with A and work all the way down the alphabet. And this is, it's not hard stuff, but it is very tedious. I don't think I'm going to make you watch all of this. I'll probably fast forward in the video, because you're going to get the gist of it real quick, and then it's going to become boring. But I will at least calculate a few of these for you. So okay, so what we want to do, we are calculating the starting font sheet byte. Starting font sheet byte equals font sheet width. Oh, we don't have a font sheet width, do we? We have this is our font sheet width times font sheet height, which is and let's see, minus font sheet width. I think that's it. I think that's all you have to do. And the reason why is because, so if you think about this, we're basically going from here, and then height times width, we're calculating it all the way to the end here in the top right hand corner, and then minus width again, which gets us back here to the top left hand corner. That's all it is. Now, to do B, on the other hand, we're going to start by copying this bit, and we're going to do, see, width times height minus width, and then we're going to skip ahead one character, so plus the character width. Now to calculate C, we are going to do the exact same thing, but we're going to skip forward two character widths. Times 2. This one will be times 3. And so on and so forth until we get all the way through our font sheet. So I'm going to basically, I think I'll probably fast forward through the rest of this. Okay, so I have finished my switch case block from hell, where we are cycling through each character in the string in this for loop right here, and then each time we are performing a switch on the character of that string, of the character that we want to print. So like the first character in the string, the second character in the string, the third character in the string, and each time we're saying, okay, what letter is it? And for each one of those, we are basically going and finding that character in our font sheet over here, in this guy. We're finding each character in the font sheet, and we're assigning that to our starting font sheet byte. And as you can see, it goes on and on and on, because you have to do this for every character. You have to do this for case sensitivity, all this kind of stuff. And you can see that it doesn't matter what the dimensions of your font sheet are, you can still work out the arithmetic pretty easily. In fact, that's kind of one of the reasons why I did the single row, like my font sheet is all in one row, is just because it makes this arithmetic right here extremely simple. But even if your font sheet was, say 12 characters wide by 13 rows or something, you could still work out that arithmetic pretty easily and do the exact same thing. You just have to go and locate each character in your font sheet. So yeah, I'm doing all the numbers, I'm doing some basic ASCII symbols. We're not going to be printing Unicode in our game, in our old school retro NES game. We're just going to be printing basic ASCII characters. I did make a couple of special cases here though. This guy right here, and when I upload this text file to GitHub, it turned it into one of those weird diamonds with a question mark in the center to represent just like it doesn't know what this character is, but it's extended ASCII BB, which is this guy right here. And this is just going to be our colored in arrow, our solid arrow to help us navigate menus. So whenever we're selecting menu items, I think this is going to be our little menu arrow to show which item in the menu that we're on. And then finally, this guy is like, I didn't even know how to type that on the keyboard, so that's why I wrote in the literally had to specify the hexadecimal, and it's just the last thing on the spreadsheet, which is this weird sort of like 50% half shaded block, because I feel like we might need half shaded blocks at some point. A good example of when these often show up, I see these a lot in retro style UIs to represent the cursor. Like if you're going to draw text that sort of like emulates someone typing, and then they'll just have like a little cursor flashing at the end of the line to show like this is where your next character will appear when you keep typing. We might use it. Oh, and then finally the default case is what if the user passes us some character that we do not have we don't have a character for in our font sheet. In that case, I'm just going to print a question mark. So if the user if the user sends us something that we don't know how to print, we'll just print out a question mark. And then optionally, I might actually assert right there and crash the game if we get unexpected input here. I don't know yet. But anyway, there you go. There is our gigantic switch case statement. Now, let's go ahead. This should be exiting the for loop. So at this point, what is left? Now we basically are going to do the exact same thing that we've already done in the blit 32 bits per pixel bitmap function by using the nested for loops that basically will draw all of our x and y coordinates and basically draw out the string bitmap. Oh wait, my bad. We need to do this right here. Right? Let's make sure I have it right here. Yeah, after the end of the switch. So we're doing this for each character. For int y pixel until y pixel is less than the height minus 1. How about that? Y pixel plus plus int x pixel x pixel is less than character width x pixel plus font sheet offset equals starting font sheet byte plus x minus starting font sheet byte plus x minus font sheet width, which is this whole thing here, times y. Okay, string bitmap offset equals this is the index of our for loop way up here. Character times character width plus we need font sheet width again times font sheet height. Oh, hold on a second. Width plus, oh, this is wrong, this is wrong, this is wrong. This should actually be not game bitmap, but string bitmap. String bitmap is our temporary game bitmap. Do plus string bitmap offset character plus height minus string bitmap dot bitmap info dot bi header dot bi width plus x. Info dot my header dot bi width times y. I think that's correct. So now we essentially just need to do two memory copies, one to copy out of the out of the font sheet, and one to copy into the font sheet bitmap. Font sheet pixel. Destination size is the size of a pixel 32. The source is pointer to pixel. Cast to a pixel 32. Where is my font sheet? Oh. Bitmap, memory, plus font sheet offset, and then the size will be size of pixel 32 again. This time we're copying that same memory into our string bitmap memory. Plus offset. Force. Okay, we did it. I think that's it. So to recap all of that nonsense, what we're doing is, imagine that I want to print, oh, I can't do it here, game over. I wanted to print that. So what we're doing is we're basically going through each character and we are appending each character in sequence to the end of our game bitmap, one at a time. The letter G, the letter A, the letter E, the space character, the O character. And then finally, once we get done with all of that, we were going to write that entire string bitmap into our buffer using the BlitStringToBuffer BPP bitmap to buffer function. So this is going to be string bitmap, and then X and Y. That ought to do it. I'll go back and fix all these warnings after a while. Okay, so I think we're done with our text function. Let's go test it out. If we go to render frame graphics, right here where we are blitting our character, let's split some text somewhere. BlitStringToBuffer, and it's going to be game over. And we'll just pick a random arbitrary location on the screen to print that. Oh, we have to specify the font sheet too, of course. G6x7 font. Pointer the address of 6x7 font. Okay. It's the moment of truth. And it seems to work perfectly. So now we have text, ladies and gentlemen. We were able to write the text "game over" on the screen. So, alright, I'm feeling pretty good about this. Let's see how we're doing on time. So, the next thing I think I want to do is, it is cool that we can draw text, but it's also very important that we be able to change the color of this text, because I'm sure that at some point in this game I'm going to be able to want to draw the text in a white color, would be the most important, but also I may want to draw the text in any other color too. Maybe I want it to be red or pink or yellow or blue or green. I may want to draw all sorts of colors of text. So to do that, and obviously I don't want to have multiple sprite sheets. I don't want to have multiple identical sprite sheets that are drawn in different colors. That would be silly. So what I think we should do is be able to, or have the capability to, modify the color of the font in code. So if I go back to BlitStringToBuffer and go all the way back down here where I am, so see, like right here, I've lifted the font sheet pixel out of the font sheet. I could modify it at this point. Font sheet pixel dot red equals, and font sheet pixel dot green equals 0. Font sheet pixel dot blue is 0. Run the game again, and the font should be red now. So yeah, I basically just need to, I'll probably just make them make these parameters, input parameters, so that the caller to this function can just tell me what color they want the font to be. Seems like the most straightforward approach. However, I think that probably puts us at the end of our time. So, and it's a good stopping place too. I mean, we have text. So the first thing I'm going to do with this text is replace the debug stuff up there. Then we will have just a little bit less reliance on the Windows API, because we won't be using those text out function calls anymore. But yeah, that pretty much does it. So, as usual, thank you for watching, and if you have any questions, please feel free to leave comments on the videos. I will address your comments in the upcoming episodes, and you don't have to post a comment about the current episode. You can post a comment on any episode, and I'll talk about it. And let's see, what else? Oh yeah, don't forget we have a GitHub repository that goes along with this code. I keep it updated in step with these episodes, so you can follow along at home. And that's all. So until next time, have a good week.